Okay then guys, let's have a little look at this section here. This is where we're going to look at the extended binomial series. There's 25 questions in this section. And the first thing we could do is perhaps we could have a look at the GP. Here it is here, put it out. A well-known GP, 1 minus x plus x squared minus x cubed. Here we see this as GP. The first term is 1, and then each subsequent term is obtained from the preceding term by multiplying by minus x. So our common ratio is minus x. Our first term is 1. The S infinity is a over 1 minus r, isn't it? A is 1, r is minus x. So that ends up being 1 plus x then, with the double minus. So we can write 1 plus x to the minus 1. And we know that that series, that infinite series, is valid provided that the modulus of x is less than 1. So, with that thought in mind then, let's have a look at the binomial series. At the moment we only use it for positive integers n, but let's put in n equals minus 1 and see what we get. So 1 plus nx is here, n is minus 1, the input x is just x. Nx, n minus 1, x squared over 2 factorial, n minus 1, n minus 2, x cubed over 3 factorial, and so on. The 3 factorial cancels, the same here with the 2 factorial, and we got a minus, 2 minuses make a plus, 3 minuses make a minus. So we end up with this series, which is precisely the series we had here. And that's what we would have expected to happen, wouldn't we, when we worked out this series, because we know it equals this sum, 1 over 1 plus x. So it appears, by inspection, that the binomial theorem works for values other than the positive integers that we tried in the previous section. And that is in fact the case. In actual fact, the binomial theorem can be shown to be true for all real values of n, any n we choose, positive or negative, fractional, irrational, any real value of n that we choose we can put in, provided that we put this condition on the value of x in that case, that the modulus of x is less than 1. And we'll end up with an infinite sequence of x's in our expansions in these cases. So, with that thought in mind, then let's have a look at this series here. Instead of our input x is now minus x, our n is still 1, so it's 1 plus nx, input x is minus 1, n minus 1, input x squared over 2 factorial, n minus 1, n minus 2, input x cubed over 3 factorial. This time there's 2 minuses. Here there's 4, here there's 6, so they all become pluses. So this is the other series that we get out straight away from the binomial theorem, when we put n as minus 1 and our input x as minus x. We're going to do these two questions in question 1 and 2 in the section, but we've just briefly gone through them here. This series holds when our input x, here's our condition, must be less than 1. And we can then rewrite that, drop the minus in the modulus, and that's the same as x being less than 1 as a modulus, isn't it? So that's when we look at these simple problems in these sorts of forms, and we have to be careful with our input x being the modulus less than 1. But when we look at a variety of problems of a more general form, say a plus x to the n, what we do in these instances is we rewrite this as we take an a to the n outside the bracket, as we've done in the previous section. And we look at this and we expand this series here and see what we get. But bear in mind that we always state the valid range. So we must state when it's valid for in these cases. And here our input x modulus must be less than 1. And we can then simplify that and rewrite it in a more easily understandable form. We simplify this inequality here and write it in this form here. X must lie in this case between a and minus a. So that's it. That's the extended binomial theorem then. All the best in this section then, guys. And hope you get on okay with it. And I'll catch you in the next section. Cheers.